So welcome to our lecture 5 of group theory. In previous lecture I have discussed till what is the inverse of an element and left inverse, right inverse, and give some examples. You have given some examples. Now the next topic which comes is called a semigroup. See, if a groupoid satisfies the associative property, then it's called a semigroup. If a semigroup, say G naught, satisfies the commutative property, then it's called a commutative semigroup. Let me give some examples. Z plus is a semigroup. Similarly, Q plus and R plus are also semigroups. Z dot, Q dot, R dot all are semigroups, but Z minus, it's not a semigroup since it does not follows the associative property. Similarly, Zn dot is also a semigroup, as well as it's also, you can see it also commutative semigroup, as it follows both the, as it's a groupoid which follows both the associative and to commutative law. Next, there is a problem on it. Say there is a theorem. Let S naught be a semigroup and A belongs to S, then e to the power m plus n is equals to e to the power m compose e to the power n. The proof is very simple. E to the power m plus n equals to a compose a compose a compose a up to m plus n times is equals to a compose a compose a up to m times compose a compose a compose a up to n times. Implies is equals to the power m composite to the power n. So our proof is done. Or we can do this by like this, a compose by taking the LHS, so taking the RHS side. I have done this proof by taking LHS equals, this is what equals to RHS. we can then do the same problem by taking RH is equals to e to the power m compose e to the power n, which is equals to a compose a up to m times compose a up to n times is equals to, we can write this a compose up to m plus n times is equals to a to the power m plus n is equals to LHS. So LHS is equals to RHS. The proof is done is in another way. The next topic is, what is a monoid? A semigroup G0 containing an identity element is said to be a monoid. G0 is a monoid if this shows these properties. First one is associative property a not b not c is equals to a b a comp not c is equal, where not is the binary operation. This is the associative property. And number 2, and there exists an element e in belongs to G such that a not e is equals to e not a is equals to a for all a belongs to the semigroup G. Then G is said to be a monoid, and if the monoid G not satisfied the commutative property, then it is said a commutative monoid. Here Z plus is a monoid with identity 0, Z dot is a monoid with identity 1, let E be a set of all even integers with the operation multiplication, set of all even integers, and we define the operation binary operation as multiplication. Then this is always a semigroup but not a monoid, as the identity element 1 does not belongs to E. Zn dot is also a identity monoid with identity element 1. A matrix of ideal matrix of all order R with the operation multiplication is also a monoid with the identity element of order 2 of matrices is the identity element, which is like this 1 1 0. Now the next theorem what we need to know is a theorem in a monoid m naught if an element a be invertible, then A has a unique inverse. So clearly for doing this proof we'll suppose there are two inverse of the element A in the monoid say A dash and A double dash. So let E be belongs to G, be the identity element of the monoid M naught, and of element A the inverse elements are A dash and A double dash. So we can, from the properties of A dash, we can say A naught A dash is equals to A dash naught A is equals to E, and by property of A double dash, what we can say A naught A double dash is equals to A double dash A is equals to E. Now if we write them like this, A dash naught A naught double dash, we can write by associative property, we can write this like A dash, since our monoid satisfies the associative property, we can write this composition like this: A dash not A dash, since not is associative, but again we have A dash not and dash is equals to A dash. Now what this becomes, from the property of this is the inverse of A, so this will become A naught E, and this is the identity element, so what will this become? A dash, and again A dash A naught A, take this thing, what to this is also inverse of A, this, so this will become E, so this the identity element, so this we can be written as E naught A double dash. What will this will become now? A double dash. So from 1 and 2, what can we can say? A dash equals to A double dash, because we will be beginning from the same things and returning from two different inverse of element A. So from the equation 1 and 2, we can say the inverse of the elements, the different inverse of the elements A are actually equal, so there exists a unique inverse of element, an arbitrary element A in monoid A not say. Then the next proof, in a monoid A naught, if an element AB left invertible as well as right invertible, then A is invertible. So what is given? There is M naught is a first of all a monoid, so there exists an identity element E belongs to M, for which A naught, for all A belongs to M, A naught E is equals to E naught A is equals to A. Again we have given some element A naught say belongs to M, which is both left and right invertible. So there exists an element A dash A naught dash such that A naught, since A is left invertible, A naught dash dot A naught is equals to E, and A is right invertible, so we can say there exists element A naught and dash and A naught double dash such that now from the property of right inverse, what we can say, A naught dot A naught compose A naught double dash is equals to E. Now we can write A naught dash compose A naught double dash is equals to A naught dash compose A compose a not double dash since it's a monoid and it follows associative property. So by this we can write this associative property, we can write this, and again a not dash a not double dash can be written as, what is this? This will, from the previous property we can write this as E. We can write this is from E from here. So this will become E not double E not a compose A not double dash. So it will become A not double dash because this is the identity element. Similarly, A dash not, this is also will become equals to E. So A not dash compose E, this is now becoming A not dash. So from equation, similarly from like next proof, from equation 1 and 2, what we are getting, A not double dash equals to A not dash. So finally what we have, so the two inverses are becoming equal. So what we can say, A equals to, so what we can say, in for the element A naught dash equals to A naught dash. So let it light, let me light in next space here, not enough space. So what we can say, A naught from 1 and 2 we are getting A naught dash equals to A naught double dash. So we can write, if we say this is equation A and equation B, now from A and B we can say A naught dash not A is equals to A naught dash is equals to E. So clearly this is the property of element to becoming invertible, as E is the identity element and A naught is the inverse left and right inverse of A. So our proof is done. Now there is a definition of unit. What is a unit? In a monoid, an invertible element is called an unit. So any element in a monoid which is invertible is called a unit. So I will end this lecture up to here. In next lecture I will ask you some examples of unit, then I will start from the topic what is a quasi-group. So thank you, I'm ending it here. Goodbye.